Let's consider this example dealing with a calculation of the energy released in a nuclear fission or fusion reaction. Considering the reaction we have here, uranium-235 and a neutron become a 141 barium and a 92 krypton and 3 neutrons. You determine whether it is a fission or a fusion based on where the biggest atom is, and the atom size is the top number. So our largest atom here is the uranium-235. It's breaking into smaller atoms. Therefore, that is a fission reaction. Now, in terms of the energy that's released, we're going to deal with E equals mc squared, but we have to find the mass defect. And so what we're going to do is get the atomic mass of each of these individual isotopes and the neutrons, combine the mass we start with before and the mass we end up with afterwards. They will not match each other. You'll always have less mass in the end. Okay, subtract to find the missing mass, and the missing mass is that mass that has been converted into energy, and then calculate with E equals mc squared. So we're going to use not a normal periodic table, but an isotope table. And if we pull that up, here is our isotope table, and right now it's on hydrogen, but the first atom that we need is uranium. And so I'm going to click on uranium. Specifically, we need uranium-235. It's not on 235 right now, so we're going to click on 235. On uranium-235, what we need is this atomic mass that's in atomic mass units. So I'm going to note that up here. 235.0439 to 9918. And then we've got one neutron. And neutron mass is a constant, 1.008665. And then that becomes a barium-141. So we go back to our periodic table. We find barium. We click on 141, and we've got the atomic mass there, 140.9144110009. And then we've got a krypton 92. So krypton 92, 190, oops, not one, how about 91.9261561 atomic mass units. And then we've got 3 neutrons. That's 1.008665 atomic mass units. So pulling that back out of the way. So now we've got the mass of everything, and now what we need to do is combine what we start with and combine what we finish with. So when we get the combination of what we started with, we get a 236.0525949. When we combine what we finish with, we get a 235.8665622. Now, they don't match. Again, the final mass is always less, so we subtract those to be able to find the mass defect. Sometimes that is represented with the symbol delta M. So we get a mass defect of 0.186032.691 atomic mass units. Now, if we're going to plug that into E equals mc squared, we have to convert that into kilograms. 1.66 times 10 to the negative 27th kilograms to 1 U. That's your conversion factor. Now, rounding this, we get a 3.09 times 10 to the negative 28th kilograms. Now we're ready to plug into E equals mc squared. So E equals mc squared, the mass we just got, 3.09 times 10 to the negative 28 kilograms, multiplied by the speed of light, 3 times 10 to the 8th meters per second, quantity squared, gives us 2.78 times 10 to the negative 11th joules, and that's the energy that is released. That energy is released because some of the mass is converted into energy. That's your source of energy in any nuclear reaction. Ponder physics.